somera mu ddiiro lyo ng'ewagiddwa. Maryland High School erisangibwa Entebbe, ssomero ly'abawala n'abalenzi. Tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga, nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory, ssaako ne computer lab wamu ne
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzannyisa by'abaana byonna mu nsi tubirina. Ate ng'abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi nga bwakayisa Buddo Junior.
wamu ne
Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Yes, a good morning to you, my dear students and all followers on this program. I want to welcome you this morning, yet for our next lesson. This Saturday, we shall be proceeding with our Section A coverage and revision of Physics 2. But before we start our lesson, allow me to remind you that Teacher Kakuru has a YouTube account that runs under the name of Teacher Kakuru. The account has videos of lessons that are taught online. Please be interested to follow as students. And those that have been following us on Let's Learn From Home on Facebook, please do. Without wasting time, I want to again encourage students that it is consistent practice that will make you a better student. Kindly, let us start from where we stopped and we proceed to see a bit of flashback. Last time we looked at deviation, and we are looking at the deviation of through a mirror. A very brief recap. We looked at that when a mirror is rotated through an angle, assume this mirror is in position 1, we saw that if it is rotated through an angle theta, before the rotation, of course, we saw that this is I, and that would also be I, which is R, and this was G. And automatically that was G also. We saw that if this mirror is rotated into a new position without altering the incident ray, say it is now rotated through this position in the clockwise direction. If it is rotated in that direction through a known angle theta, then without altering this, it means that the glancing angle of the ray has decreased. Here, if we look at this as the new position of the mirror, this would be the new glancing angle. So it will have decreased by this angle theta to G minus theta. And we are able to see that the deviation, the new deviation of the reflected ray or the rotated ray would get another ray 2. And that new deviation, we're able to see, if I call this new deviation D2, it would be equivalent to 2 into G minus theta, 2 into, it would be equivalent to 2 theta. Since we looked at it anyway, I'm not going to go back to that. Now today I want us to start by looking at the applications of this principle. There are 2 applications of this principle. I will briefly talk about one, and ask you to look at the other. This principle of rotation of the mirror through an angle theta can help us to determine through what angle a given device will rotate. And one of the applications, it is used in the optical mirror galvanometer. It is used in the optical mirror galvanometer and also used in the sextant. Under the optical mirror galvanometer, we shall be able to see that the optical mirror galvanometer actually works as a massless pointer in some instruments, especially if it is detecting very small currents. If it is used to detect very small currents, that we can have a mirror here. We must use a light beam. We must use a light beam. If I use my first mirror here, I will have a light beam here. The light beam will be incident normally. Now, if I have my light beam coming from a source, it will be incident first normally. Therefore, it will pass through, assuming this is my mirror in that position. And that the distance from this point, we are going to call this distance d. This light will be incident on the mirror. And because it is incident normally, it will be reflected back along the same line. Now, if this mirror is rotated into a new position, position 2, through an angle theta, as I have said, we are applying this very principle. If it is rotated through an angle theta, then the reflected ray now will be the incident ray will now be reflected at an angle here, which we are supposed to be able to show. But that angle of reflection is, since it is applying this principle, it will be reflected at an angle that is actually twice the angle of rotation of the mirror. Now, the most common question that can be brought here is they can ask us to find the displacement it causes along this line. They can ask us to find the displacement it causes along this line. This is supposed to be a scale. So we are able to measure. If this is a scale, we are able to measure this distance y. But ideally, a light beam that is incident normally will be reflected along the same line upon hitting the mirror in position 1. And if the mirror is rotated through an angle theta, the incident reflected ray now will be, the incident ray will now be reflected at an angle that is twice theta. So using some trigonometry knowledge, we are able to generate an expression that relates the displacement of the reflected ray from the initial point, the distance d between the scale and the mirror, and the angle. So if we use the tan of 2 theta, we shall be able to get tan is opposite over the adjacent. We shall be able to get y out of d. And if our interest is to find y, our y will be d times the tan of 2 theta. But the angle of rotation is assumed to be very small. That for small angles, the tan of an angle is approximately equal to that angle. So for small angles, our y will, of course, be obtained now equivalent to d times twice the angle. And if our interest is y, we would be able to get y. If our interest is d, we would be able to get d as y out of 2 theta. If our interest is theta, we would be able to get theta. So ideally, this expression allows us to determine theta by making theta the subject here. We get theta as y over 2 times the displacement. Because we are supposed to use this to say if the mirror is rotated through an angle theta, what would be the value of that angle? In other words, the optical lever mirror galvanometer can be used in electromechanical devices to allow a small current flow in a circuit, and that current causes a small diffraction. And therefore, because of that purpose, it is used in pointer instruments, especially like the galvanometer. For the students that are following, when you start doing experiments that require you to use a galvanometer, you may be able to take a keen look at the galvanometer. On the scale, you'll be able to notice there is a mirror. There is a mirror, and the purpose of that mirror is to enable a very quick, light, or massless diffraction of the pointer. I will ask students to look at the sextant, but I will mention for direction and guidance that a sextant is a device that is used to look at distant objects. It is a device that is used to look at distant objects, and it still applies this principle of rotation of the mirror. It applies the principle of rotation of the mirror. And basically, for the sextant, we have the mirror. We have the object, for example, the sun, that is supposed to be seen. And you have a ray moving from the sun and the incident on the mirror. Now, if the mirror is in that position, this ray is going to be reflected off, but we have another ray, for example, moving from a horizontal point. Now, these mirrors, if the mirror is in that position, for example, position 1, this ray is going to be reflected off here. We'll consider a ray from the sun and a ray from a point or object H. So there is a mirror here, but this mirror here is supposed to be half silvered. And therefore, this side here will have a telescope. So this ray will be reflected into the eye of that individual. Now, when this mirror is rotated to a new position through an angle theta, this same ray is now reflected off again through this, but appears to be reflected still to the telescope and to the observer, who is this side, and in the process causes an image of this object to be seen. So students are encouraged to look at how the sextant can be used in verification to show the rotation of the mirror and ultimately allow us to see distant objects. That is an assignment I am leaving for the students to find out. But before I proceed, I also want to ask the students to find out what are the advantages of using the optical mirror galvanometer. Why the optical mirror galvanometer? Why is this half a mirror? Why is half of this mirror shaded and the rest not shaded? In physics, I want to remind you that the most important part in an experiment description is a correct diagram. We call it a working diagram. And once your diagram is working and you know what you're expected to do, then a very straightforward explanation of how the diagram works is required, and of course your diagram must be correctly labeled. Where there is a need for a label, you must be able to label. Here we use a light beam. A light beam of light is incident normally through the scale and reflected normally with the mirror in position 1. When the mirror is rotated to position 2, the same light beam now will be reflected at an angle that is twice the angle of rotation, and the beam will cast its image at a displacement y, and you're expected to find an expression for the angle of rotation there, which can be obtained as indicated. Question is, you can be asked to describe, how do we ask this? You can be asked to describe the mode. Describe the mode of operation of the optical mirror galvanometer. That is A. B, describe how a sextant can be used to focus distant objects. If they say distant objects, they don't say distance objects, they could use any of the two. They can say, describe how a sextant can be used to focus the sun. To focus the sun or to focus the stars. Now we are going to look at the refraction, the type of refraction that we call successive refraction again, on plane mirrors. We shall look at it as deviation due to successive refraction. Deviation as a result of successive refraction at two inclined mirrors. Deviation as a result of successive refraction at two inclined mirrors. Before I look at that, I want to start by referring you to this. For the ordinary level students and all the students in high school that are attending this class, you may recall that there is a common question here that probably has been asked. This question must be asked by every serious teacher for students that are between senior 1 3rd term and senior 3. That if this is a mirror and this is a mirror, and these two mirrors are inclined at a known angle, for them they will give them a known angle, for example, say 70 degrees, and they tell you a ray is incident, say at 40 degrees, and they ask you, 1, complete the diagram. Or if they have completed the diagram like this, they can ask you to determine various angles, maybe A, maybe B, and so on. So it is this principle that you learned at O level that we apply now on the diagrams we are going to look at. Let me look at the first case. If these are two mirrors, as I've already described, that is mirror 1, this is mirror 2, and they are inclined at an angle theta. They are inclined at an angle theta. In the first case, if I have light incident at this point, I'll call this point A, and it is definitely reflected off. It is incident at a non-glancing angle. We can call this angle beta. This is a glancing angle. It will be reflected in accordance to laws of refraction, that this angle here will definitely be equal to that angle here, and the glancing angle, however small it may appear on the diagram, is supposed to be the same as you are aware. This glancing angle, if I let this be better, even this will be better. If this light is reflected inside like this, then our task is to find the deviation. And that means that if this light is incident here, assuming there was no mirror, it would have passed through as I am indicating. And that means that this angle, I will be magnifying this later, this angle beta, by looking at angle geometry, is equal to this other angle here, beta. And therefore the deviation that we are going to look at point A is going to be beta plus beta. But if this light is incident here, and we let the angle there be alpha, if the angle here is alpha, it will still mean this angle is alpha, because again it is a glancing angle. It is again a glancing angle. Now if this is extrapolated, the deviation here is supposed to be that. And this angle here is opposite again this angle, and therefore it is also alpha. It's also alpha. So if we extrapolated this to this point, this would give us the total deviation. It gives us the combined deviation between here and here. And our task is to show or to derive the expression for that deviation. I want to call this point B, and I said I'm going to amplify these diagrams. At point A, I am amplifying what happens at point A. If this is the ray, because this number normally disturbs students and it's very popular, and I'm saying it is reflected off. So if this is better, what I want to emphasize is that if this light ray went all through, this is what we want. What I'm going to call deviation D1. So if this is better, this is also better. This one. And by angle geometry, these lines crossing each other like this. This angle is equal to that angle. So this angle is equal to this other angle in here. And the deviation is that, what I'm calling D1. So D1 is actually equal to beta plus beta, which is 2 beta. But you see the direction. It is in an anti-clockwise direction. And when we are dealing with angles in an anti-clockwise direction, the angles are considered to be positive. Because the ray goes this side, the deviation is from here, it is in a clockwise direction, sorry. And therefore, it is negative. So my D1 is going to be 2 beta, and we'll say, since it is clockwise, it is negative. But if I put clockwise in brackets, I can keep the negative silent. I can keep the negative silent. And now we look at this point. At point B, This is the lower point here. I will take it like that. Light is incident and is reflected off. And this is our mirror. And if we extrapolate this, assuming that there was no reflection, this is the deviation we are looking for. And this time it is anti-clockwise. But we said this angle is alpha, and this angle would definitely be alpha since glancing angles are equal. But this angle is also equal to this angle, so this is alpha. So the deviation d2 here will be 2 alpha, and it is in an anti-clockwise direction. I can use this arrow to illustrate anti-clockwise. We could also use an arrow here to illustrate a clockwise. So the total deviation that we want which I can call D, is supposed to be the sum of these two deviations. But if I come back to my triangle, assume this point is C, if I come back to my triangle, I want you to note that this triangle A, B, C has beta and theta as interior angles, and alpha is an exterior angle. So we can call this an equation and also say that from triangle ABC, two interior angles are added to give us an exterior angle. Two interior angles are added to give us an exterior angle. And therefore, as I finalize, if I get my total deviation from A, my total deviation, D, will be equal to my D1, which is 2 beta. We are saying it is negative, plus 2 alpha, negative because angles measured in an anti-clockwise direction are negative. D1 is, yes, negative. Angles measured in a clockwise direction. And therefore it means our D is beta 2 into beta minus alpha. That is still equation A. But from B, from equation B, my beta minus my theta, if made the subject, is the same as alpha minus beta. My theta is alpha minus beta, and therefore if we look at this deviation here, D1 is 2 beta, that is positive. D2 is 2 alpha, this is negative. It is the alpha that is negative because it is the anti-clockwise. Therefore, this expression becomes beta minus alpha. D2 is 2 alpha, and that is negative. 2 beta is negative. Sorry. 2 beta is negative, so it's like this. So we have alpha minus beta here. Yes. And our theta is alpha minus beta. I want to emphasize that when angles are measured in a clockwise direction, they are positive. And when they are measured in an anti-clockwise direction, they when they are measured in an anti-clockwise direction, they are positive, and when they are measured in a clockwise direction, they are negative. So it implies that if we substitute here for theta in A, we obtain our deviation as 2 into alpha minus beta is now theta, which gives us 2 theta. So the deviation here is 2 theta, and as you notice, the total deviation, since it is positive, it implies that it is in an anti-clockwise direction. So we are supposed to show that the total deviation is actually equivalent or given by 2 or twice the angle of inclination. As you can still see, when 2 mirrors are inclined at an angle theta, the refracted ray is deviated through twice the angle of inclination, is equivalent to twice the angle of inclination. There are 2 cases. That is case 1. I'll give time for the students to capture the solution or to study the solution. Since we started here, I will clear this space, assuming that it is what we started with, and prepare it for our next case. The cases are slightly different, and what makes them different is the diagram. In the second category or case, we still consider mirrors inclined at the same angle theta. I hope this will be a little faster. I'm not going to put emphasized diagrams to clarify. But what happens here now is that incident light at an angle that we shall fit in, you can put there in later, will be refracted and will ultimately be refracted out. Will ultimately be refracted out. The other one was refracted inside. This is refracted out. If I let the angle here be alpha and the angle here be beta, the diagram sketch setting may not portray that these angles are actually equal, but that is the concept, the factual concept we apply, that incident light is reflected at the same glancing angle. And of course, our interest is to find the deviation. At this point, we extrapolate, and our interest is to find the deviation here, which will be that one. And here, if there was no reflection, this would continue, and our deviation would be that. You notice the deviation in this diagram is all clockwise. If we call the deviation here D1 and the deviation here D2, I think calling this point A and this point B and point C, my dear students, you should be able to note that there are a few differences. At A, I can say the deviation, which I'll call D1, is clearly, this angle is still opposite that angle, so it is still 2 alpha, and this is in a clockwise direction, so it is positive. And at B, the deviation, since this is beta, looking at these 2 opposite angles, this is also beta. At B, the deviation is also, which I'll call D2, is also given by 2 beta. It is also in a clockwise direction. So to find the total deviation, I will simply add total deviation, if we call it D, it will be D1 plus D2, and our D will of course be 2 alpha plus 2 beta, which we shall write as 2 into alpha plus beta. But we have a triangle there. We have a triangle ABC. We have a triangle ABC. And this time around, our triangle has interior angles. All of them are there. If I consider this triangle, ABC, I can even sketch it out. It looks like this. Of course, this is a right ray, but this angle is alpha, this angle is beta, and this angle is theta, implying that alpha plus beta plus theta will add up to 180 degrees. And since we are interested in alpha plus beta, the alpha plus beta will be 180 less by theta. So if we substitute in equation, if I call this equation 1, I would say in equation 1, our total deviation will therefore be 2 into 180 minus 2 theta. And this will be equal to 360 minus 2 theta. Now, that's where I want to explain. This is 360 minus 2 theta in the clockwise direction. In the clockwise direction. But we could say that D is also equal to 2 theta in the anti-clockwise direction. I want to emphasize that one using a simple illustration as we come to the end of that part. That whenever we say that an angle, we are all aware that if this is a circle, its angle sum is 360. So if I took off, say, from here, if I take off 2 theta, if I let this be 2 theta, it means that the angle we are calling 360 minus 2 theta is this, in that direction. And this angle will definitely be equal to 2 theta in the other direction. So we are saying that 360 minus 2 theta degrees is equivalent in the clockwise direction is equivalent to 2 theta in the anti-clockwise direction. Sometimes they may ask you to show that actually the deviation is twice theta, and candidates may, when they get to this step, they may wonder how to reach this conclusion. This is the same as this, but this is in a clockwise direction, whereas it is equivalent to this in an anti-clockwise direction. As you capture that, we can prepare to look at our next concept. Our next concept. We can prepare to look at our next concept so that we can see whether possibly today we can wind up plane mirrors. To the students that may not be in high school and probably awake and following this lesson, I want to say that most of the concepts we are using here are basically angle geometry concepts. And if you are able to learn an idea here, and you intend to do physics at high school, I can assure you that you should not delete anything. I also should be able to emphasize to any student that intends to do physics at high school that physics concepts do not change. What you study at O level is what will be amplified at A level. Most of the concepts that are standard will stay. The definitions, the laws, the principles, the experiments. What only happens is that you go a little deeper when you go to high school. Plane mirrors, I want us to move to plane mirrors and quickly make a point on images, properties of plane mirror images. Of course, images formed in plane mirrors have various properties, and one of them is that they are the same size as the object. They are the same size as the object. They are laterally inverted. They are virtual. They are the same distance. Behind the mirror as the object in front of the mirror. We also usually say that lines joining corresponding parts of the object to the image bisect or cut. They bisect the mirror at 90 degrees. Lines joining corresponding objects bisect the mirror at 90 degrees. But ideally, the first four are very key. The first four are very key. And in that interest, therefore, there is a common question that they normally ask you to show that the object distance, which I have indicated as number 4, is equal to the image distance for a plane mirror. So we can be asked to show that the object distance is equal to the image distance in a plane mirror. And we will require a simple diagram here. I will use only one light ray. I'll consider point object. I have already shown in a previous illustration that if a ray is incident normally, it is reflected along the same path, but extrapolated this side. And from this same point, if we have a ray incident to the mirror, it will be reflected off. And it appears to an observer that is here, it appears to be coming from this point. So if we label this diagram carefully, then we can be able to verify. We can call this point A, point D, point I, and then if I call this point O, then the angle here can be called the angle of incidence, and this is definitely 90. This would be 90 minus I, and that means this would be I. In other words, if this is a horizontal line, which is our normal, these two angles are alternate. Angle DAO, and if I call this N, angle AON, they are equal. Then when I come here and say this is 90 minus I, this is still I. But when you look at this, since this is the refracted ray, and we are interested in this angle, this is already 90, this angle here is supposed to be the same as this. So if this is R, this is 90 minus R, and this is 90 minus R, so this is R. If we label this that way, we can be able to show that angle D A O is equal to I, and this angle we are saying is equal to angle AON, and also our angle from here, this is R, but ideally R is equal to I. That's what we want to actually confirm. If these two triangles are congruent, this R is equal to I. And therefore, if I look at the value of I can say angle N, if this is B, N or B is equal to angle A O N. I can cite laws of refraction. Because this angle is equal to this angle, according to the principle of laws of refraction, it automatically implies that this angle is equal to that angle. And if that is true, then we can actually arrive at a conclusion that this distance or the triangle, these triangles are the same. I could even say that sine, because I'm interested in this, sine of 90 minus I in this triangle will be equal to AD over AO, and I can get that is triangle AOD, and in triangle DIO I can get the sine of 90 minus R being equal to DI or ID over OI. And of course, since we are saying that I is equal to R, and these distances, these angles are equal, then we can consequently conclude that the distances AD and ID are equal. Since triangles AOD and DIO are congruent, we can argue that DI is equal to AD, which actually confirms DI is equal to AD because AO is also equal to OI. So the object distance, which would actually be AD with this as the object, is equal to the image distance with that as the image. And definitely the students should be able justify that by putting that statement there, that since OD, since AD is the object distance and DI is the image distance, with the triangles AOD and DOI congruent, then we can verify that the object distance is equal to the image distance. That is a very common question. You can fine-tune it in your free time and ensure that you are actually able to go through it. Now, candidates should note that plane mirrors do not only form virtual images. Plane mirrors can also form real images. And for us to demonstrate that a plane mirror forms a real image, we can use a simple diagram where we assume that the light rays that we are going to use here are going to come from infinity. If the light rays are coming from infinity, we can be able to form a real image because they will be reflected to converge at a point where I am assuming I have my image, but they are purportedly coming from an imaginary object, which is, of course, definitely a virtual object. So we have an object here. This object is virtual, and we have an image here, which is real, if this is a mirror. The other common problem that students have is they can draw a diagram like this without illustrating that actually they have a mirror. That will definitely score no marks. That will score them no marks. You must be able to label that you have obtained a real image, but the image is coming from a virtual object that you use rays from infinity. They are reflected, but they appear to be coming from a virtual object, consequently giving rise to an image that is real. As we wind up our lesson, you may realize that time is fast spent. We can look at one last concept. Most people must have always wondered why it is possible for someone to see their full image through a mirror that is not equivalent to their height. I want to wind up with that part, and I will assume that I have a mirror. I'll give it length y, and I want someone whose height I am going to, okay, let us just look at someone's height. We have someone whose height I'm going to call y. Yes, we are coming to the end quickly. If this person's eyes are a distance x away from their head, and this is the mirror we have, we simply need to take a light ray from the head. Let that light ray, of course, go to the eye. We assume this is the eye. And the light ray from the bottom part, the foot, will also go to the eye. Now, this question is, again, common for both O and A level. If we introduce a normal here, it divides this x into a half and this into a half. And the normal here will divide this y into a half. This is now x minus y. Okay. If this was y, this is y minus x, a half, y minus x, a half. This would be an assignment for you to complete. The part that the person needs to see their face is only this. And that means if the person was of the height y, if we calculate, we have y minus x over 2 plus y minus x over 2 will be equal to the mirror size. And if we simplify, you will discover that if the I was x away, the person was y plus x. This is y plus x, if the y is up to the I. So if we add, we have y plus y minus 2x out of 2. And we shall discover that the person needs just this and this. He needs y minus x plus x over 2. And the person will need only half. This is y minus x plus x over 2. And this will give us y over 2. So if the mirror is y, you need only half its height to be able to see yourself. You need only half its height to be able to see yourself. As we wind up, in my final remarks, I want to challenge these students to prove this. Let me write this quickly. I will simply draw the diagram. This is an exercise that I want you to try out. I have two mirrors. They are inclined at an angle. And that is the diagram. This angle is 65. And these are mirrors, remember. And this point is O, this is P, this is Q, and we can call this R. I want you to determine the value of R, assuming this angle is theta. Determine the value of theta. Take note of that diagram. Determine the value of theta. If two plane mirrors, I have not written the wording in the interest of time, two plane mirrors are inclined at 65 degrees to each other. A ray is incident on one mirror, ray OP, and is reflected as indicated through QR. Determine the value of theta. I will also ask you to show that for a ray incident normally on a mirror, the angle of deviation is twice the angle of incidence. The angle of deviation is twice the glancing angle. When we meet next, we shall be starting on curved mirrors. I want to thank you for attending this lesson. I want to ask you to keep sanitizing, stay at home, and keep revising. I wish you the best. Teacher Kakuru, don't forget that YouTube account. It has several work that can make you the best student you want to be. God bless you.
somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts and sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne
Kids Kingdom Kindergarten and Daycare. Ssomero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzannyisa by'abaana byonna mu nsi tubirina. Ate ng'abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi nga bwakayisa Buddo Junior.
Fellow Ugandans, thank you for being patient and mindful of others during this very difficult lockdown due to